By the end of this lesson, you will be able to identify the 4 nitrogenous bases in DNA and classify them as purines or pyrimidines, explain how base pairing works, including the number of hydrogen bonds in AT and GC pairs, understand Chargaff's rule, and apply it to determine base percentages. Recognize the importance of base pairings in DNA replication, PCR, and overall stability of the DNA molecule.
Hi everyone, my name is Raisa and welcome to the G-nius Review Center. In this lecture, we'll be talking about DNA base pairing rules. Before we dive in, let's warm up with a quick question. Can you name the nitrogenous bases in DNA? You can pause the video and think about it. Okay, so the first one is adenine, followed by guanine, then thymine, and lastly, cytosine. Now, can you tell me which one you think are the purines and which one you think are the pyrimidines? First of all, purines and pyrimidines are the 2 main classes of nitrogenous bases that are essential components of DNA and RNA. Purines have a double ring structure, while pyrimidines have a single ring structure. Based on that, try to observe these 4 and tell me which one you think is which. I'll give you a set. If you said adenine and guanine are the purines, and thymine and cytosine are the pyrimidines, then you're right. So, adenine and guanine are the purines because they have a double ring structure, while thymine and cytosine are the pyrimidines as they both have only one ring structure. Now, a common question in genetics is who pairs with whom? Who does A pair with? And who does G pair with? So, I'll give you a sec to guess on which one you think is which. If you said adenine pairs with thymine and guanine pairs with cytosine, then you're right. Here, adenine pairs with thymine through 2 hydrogen bonds, while guanine bonds with cytosine to 3 hydrogen bonds. Now, question, which one do you think is more stable? The AT bond or the GC bond? That's right, it's the GC bond. This one is more stable as it has more hydrogen bonds. This is crucial because stronger bonds contribute to the stability of the DNA molecules. So just like a bicycle, a 3-wheeled bicycle is more stable compared to just 2 wheels, so making GC more stable. Also, take note, a purine always pairs with a pyrimidine. Why? This keeps the spacing between the 2 DNA strands consistent and uniform, maintaining the double helix structure. To clarify, purines will not pair with other purines. Similar to pyrimidines, pyrimidines will not pair to other pyrimidines. It's always one purine and one pyrimidine.
Now it's your turn. Let's apply everything you've learned so far. Here's a single strand of DNA. Your task is to build a complementary strand. Pause the video and try it yourself first. Then press play when you're ready to check. Okay, let's check it together. Let's match each base using the rules. A pairs with T, G pairs with C, C pairs with G, T pairs with A pairs with T, and C pairs with G. So the complementary strand is this. Let's do one more for good measures. Pause and give it a try. Let's solve it together. G pairs with C, C pairs with G, A pairs with T, T pairs with A, T pairs with A, and A pairs with T. So the complementary strand is this. If you nailed it, give yourself a pat on the back. Now that we established that adenine bonds with thymine and guanine bonds with cytosine, here's a question. In a DNA strand, if there was 40% adenine, how much do you think thymine would there be? I'll give you a sec to guess. That's right. there would also be 40% thymine. Another, if there was 20% guanine, how much do you think cytosine would there be? That's right, also 20%. This leads us to the Chargaff's rule. The Chargaff's rule was discovered by Erwin Chargaff. He discovered that the amount of adenine there is in a DNA strand is always equal to the amount of thymine. Similar to guanine, the amount of guanine there is in a DNA strand is always equal to the amount of cytosine in a DNA strand. That means in any DNA molecule, the amount of adenine is always equal to the amount of thymine, and the amount of guanine always equals to the amount of cytosine. This reinforces how base pairing is precise and predictable, and it plays a key role in DNA structure and function. Before we move on, let's answer this question. If a DNA molecule contains 35% adenine, how much cytosine is present? A. 15%, B. 25%, C. 30%, or D. 35%. You may pause the video if you need more time. Now let's answer it together. Remember, the amount of adenine is always equal to the amount of thymine, therefore making thymine also 35%. Now we're gonna add adenine and thymine together to find the bond percentage. 35 plus 35 is 70%, so AT bond is equal to 70%, leaving 30% for the GC bond. Now that we know that the GC bond is 30%, all we need to do is find the half to find the cytosine percentage. The half of 30% is 15, therefore making guanine 15% and cytosine 15%. So the final answer here is A with 15%. Let's do one more. In a DNA molecule, it has 22% guanine. How much thymine is present? Your choices are A, 15%, B, 18%, C, 25%, or D, 28%. You may pause the video if you need more time. Let's answer together. As we know, the amount of guanine is always equal to the amount of cytosine, therefore making cytosine also 22%. Now let's look for the bond percentage. 22 plus 22 equals to 44%, making the GC bond 44%, leaving 56% for the AT bond. Now, to look for the thymine, we need to find the half of the 56%. So half of 56 is 28, making 28% adenine and 28% thymine. Therefore, the final answer is D, 28%. Now, can one nitrogenous base exceed more than 50%? The simple answer is no. In double-stranded DNA, no single nitrogenous base can ever make up more than 50% of the molecule. Why? Because of the Chargaff's rule, which tells us that adenine always equals to thymine and guanine always equals to cytosine. So if one base increases, its pair must increase equally. Let's say cytosine is 51%, then guanine would also be 51%. That's already 102%, which is impossible, since the total must always be 100%. The maximum a single base can reach is just under 50%, and that's only if its pair dominates the composition. So remember, no base can go over 50% in double-stranded DNA.
Why is base pairing important in replication or PCR? Base pairing is not just a trivia fact. It's essential in real-world processes like DNA replication, transcriptions, and PCR. Here's a quick look at DNA replication. Enzymes to read the original strand and add complementary bases. This process relies entirely on accurate base pairing. So what if bases mismatch? Errors in base pairing can lead to mutations, failed PCR reactions, or faulty proteins. So remember, base pairing ensures the integrity of genetic information. It's a small rule with a huge implication for life, medicine, and biotechnology.
Before we end, let's have a quick summary of everything that we learned. In this lesson, we explored the 4 nitrogenous bases in DNA: adenine, thymine, guanine, and cytosine. These are divided into 2 types, which are the purines, the Ag with double rings, and the pyrimidines, which is the T and C with single rings. We also learned that A pairs with T through 2 hydrogen bonds, and G pairs with C through 3 hydrogen bonds, making GC bonds stronger and more stable. Importantly, a purine always pairs with a pyrimidine, which maintains the uniform structure of the DNA double helix. Through the Chargaff's rule, we understood that the percentage of A is always equal to the percentage of D, and the percentage of G is always equal to the percentage of C in double-stranded DNA. This also means that no single base can exceed 50% of the DNA composition. If one base increases, its pair must too, and their total cannot exceed 100%. Lastly, we saw how base pairing plays a vital role in DNA replication, transcription, and PCR. Accurate base pairing keeps our genetic codes intact, while errors can lead to mutations and failed cellular processes. Now you know that base pairing isn't just a textbook fact, it's a fundamental principle that holds the blueprint of life together.
Thanks for watching, and keep exploring the wonders of DNA. Together, let's crack the code of science the genius way.